Say you're using a chat application. You type a message and send it. Then immediately you type a correction and send that too. Two messages, sent one after the other, a second apart. On the other end, they arrive in the wrong order. The correction lands first, the original message appears beneath it. The conversation reads backwards. You might find this surprising. Chat applications run over TCP. TCP guarantees ordering. So how did two messages sent in sequence arrive in the wrong order? The answer is that TCP did exactly what it promised. The guarantee held perfectly. What failed was an assumption about how wide that guarantee is, an assumption most people make. Reasonably, because nobody ever explained exactly where the promise stops. This is a video about the boundary, where the ordering guarantee lives, what it covers, and why everything outside it is someone else's responsibility. Start with what TCP actually promises. When a connection is established between two machines, TCP creates a byte stream. Every byte transmitted through that connection has a position in the stream, a sequence number, counted from the connection's starting point. What TCP guarantees is that the receiver will see those bytes in sequence number order, continuously, without gaps. If byte 401 arrives before byte 400, the receiver holds 401 and waits. When byte 400 arrives, both are delivered in the correct order. The application receives a clean, ordered sequence of bytes, regardless of what the network did in transit. This is a strong guarantee. It means the application never has to think about reordering or loss within a connection. Whatever arrives at the application layer is correct, complete, and ordered, or it hasn't arrived yet. That simplicity is enormously valuable. Enormous amounts of the internet work correctly because of it. But here is the precise boundary. The guarantee is about bytes within a single TCP connection, not messages, not requests, not conversations. Bytes within one connection. Return to the chat application. Modern applications don't necessarily use a single persistent TCP connection for everything. They might open a new connection for each message, or use a pool of connections and assign requests to whichever one is free. If your first message goes out over connection A and your second goes out over connection B, TCP's ordering guarantee applies separately to each connection. Connection A will deliver its bytes in order. Connection B will deliver its bytes in order. But TCP makes no promise whatsoever about the ordering of connection A's data relative to connection B's data. If connection B's message happens to travel a faster path and arrive first, TCP has not failed. TCP did exactly what it promised. The ordering guarantee simply doesn't span connections. This is the first and most common place where assumptions about ordering overreach the actual guarantee. There's a related failure mode that appears even within a single connection. HTTP, the protocol that carries most web traffic, runs over TCP. But HTTP allows something called request pipelining, where a client sends multiple requests over the same connection without waiting for each response before sending the next. The requests go out in order over the byte stream. TCP delivers them to the server in order. So far, so good. The guarantee holds. But the server can process those requests at different speeds. A fast query and a slow database lookup, sent in order, might complete in reverse order. If the server sends responses as they complete, rather than in the order the requests arrived, the client receives them out of the original sequence. TCP ordered the bytes. The requests arrived at the server in order, but the responses came back in a different order. At no point did TCP fail. The ordering broke at the application layer, in the logic of how requests were processed and responses were sent. TCP's guarantee ends at the byte stream. What applications do with those bytes is beyond its scope. Here's an analogy that captures the shape of this boundary. Imagine a postal service that guarantees the letters in any single package will arrive in the order they were packed. That's a real guarantee, carefully enforced, reliably delivered. But if you ship your letters across two separate packages, the service makes no promise about which package arrives first. And if the recipient reads the letters and then chooses to reply in a different order than they were received, that's entirely outside the postal service's concern. The guarantee was about the letters in the package. It was never about anything else. TCP's ordering guarantee is exactly this scoped. Within a connection's byte stream, order is preserved. Across connections, there's no promise. At the application layer, ordering behavior depends on how the application was written. Why is the boundary here rather than somewhere broader? Because TCP is a transport protocol. Its job is to take bytes from one end and deliver them in order to the other end of a single connection. Coordinating the ordering of multiple parallel connections or enforcing ordering guarantees across application-level requests and responses would require TCP to understand the semantics of the data it's carrying. To know that these bytes constitute a request and those bytes constitute its corresponding response, to know that this connection and that connection are part of the same logical conversation. TCP doesn't know any of that. It moves bytes. The meaning of those bytes, what constitutes a message, a request, a transaction, lives at the application layer, which means ordering guarantees that span those concepts have to be built at the application layer too. Some protocols do exactly this. They assign sequence numbers to messages, track which requests correspond to which responses, enforce ordering across parallel channels. This is application-level ordering, and it's a separate engineering problem from transport-level ordering, using the same concept but built for a different scope. What the combination gives you, TCP's byte stream ordering plus whatever application-level ordering the software implements, is a layered guarantee. Each layer handles exactly what it can see. TCP sees bytes in a connection. The application sees messages, requests, sessions. The ordering guarantees are right-sized to the layer providing them. What you can see now is that the TCP ordering guarantee is not weaker than advertised. It is exactly what it says it is: complete, reliable, carefully maintained. The confusion comes from asking it to cover more than it was designed to cover. Once you understand the boundary precisely, you stop being surprised when ordering breaks above it. You start asking the right question. At which layer did this ordering assumption live, and which layer was actually responsible for enforcing it? Almost always, the answer points not to a failure of the guarantee, but to a gap between what the guarantee covers and what the application needed. Closing that gap is the application's job. TCP already did its part.